A very good morning to everyone. We will begin this important day by offering up prayers to the Goddess of Knowledge and Wisdom by singing the Saraswati Vandana. May I please request all of you to please stand.
पूरा इवेंट मतलब अरे ये क्वेश्चन पूछेंगे फैकल्टी ये सब कुछ कवर करना। बात करो यार, यहाँ किसी को भेजो, मैं फंस गया। करने के लिए बोल रहे हैं फैकल्टीज वगैरह, उसने मेरे को फंसा दिया। अरे नहीं कर रहा, वो मना कर रहा है। एक बार अमित को बोलो विशाल से बात कर लेगा। नहीं है ना?
All of you to please put your mobiles on silent mode. Thank you. I request Sonal Bhadoria to present a bouquet to our distinguished speaker, Professor M.S. Ananth. Thank you, Sonal. On behalf of UPES Dehradun and the Indian Institute of Chemical Engineers, UPES Student Chapter, I take this opportunity to welcome all the dignitaries, esteemed teachers and my colleagues to this distinguished lecture to be delivered by a very eminent chemical engineer, Professor M.S. Ananth, FNAE and former director, IIT Madras. I also welcome Professor Ananth, who has very kindly accepted our invitation. We are truly honored by your presence, sir. I now take the privilege to invite our campus director, Professor Sri Hari, to formally introduce the distinguished speaker.
Thank you. Very good morning to all of you. It's indeed a pleasure to welcome Professor Ananth to this campus. I have a couple of very interesting anecdotes about him which I think are relevant today. My first known interaction with him was in a higher education summit in IIT Madras, which was organized by Professor Natarajan. And in that I recall he made it a point that India was the first one to start the distance education and Eklavya was the first distance learner. Sir, welcome to the land of the first distance teacher, the Dronacharya. This happened in, he is supposed to have done all his penance in Dehradun. Professor Ananth is a gold medalist from AC College of Technology and did his PhD in chemical engineering from University of Florida, USA. And that is another interesting factor. A great chemical engineer coming to a university which was started by chemical engineers. The chancellor is a chemical engineer, the vice chancellor is a chemical engineer, the founder dean was a chemical engineer, including the dean who followed him. And sir, this is a university since the chemical engineers think the world of themselves, everything that happens is around that chemical engineering. So this is a university started for everything that happens around chemical engineering. Welcome to this university once again. There are a lot of credits which I'm sure will make a very interesting reading, but then we would not have time to listen to the person himself. So I will only tell a few things which are very, very important. Professor Ananth, he was the architect of National Program on Technology Enhanced Learning, NPTEL. The lectures are available today. The IIT Madras was very important institute which led this program. And the second is the popular IIT Madras Research Park, which is an example by itself to his credit. He has had many awards, including the Hadelia Prize, then the R.W. Faheen Alumni Award, and Outstanding Achievement Award for R&D sector by Chemtech, and so on and so forth. But as a person and a human being, he is much more charming and interesting. And there is no way I can bring out all his qualities. So ladies and gentlemen, allow me to invite Professor Ananth. Sir, we are all yours for the next 1.5 hours, whatever time it takes for you to. Can you move the chairs on the side so that people can see the slides?
Very good morning to all of you. I want to thank UPES for inviting me here. Particularly my friend Professor Santosh Gupta. I've known him only for 40 years. He's told me about this earlier, and I'm really honored to be here for this distinguished lecture. I want to thank the Chancellor, the Vice Chancellor, Campus Director, and so on. All the employees here for the warm welcome that I've received here. I'm going to talk today about thermodynamics in the chemical industry, and I think as we go along, I'll cover the following topics. I'll talk a little bit about the chemical industry, and you will find thermodynamics people have a great contempt for detail. What thermodynamics does is always try and draw an envelope that's so large that you can get away with few statements about the system. Then I'll talk about thermodynamics itself. And I'd like to talk about the masters and their ideas. One of the things I've been insisting in all the courses is that we should talk about the people who did it. And sometimes a little bit about their private science. Very often, great masters also make mistakes. And if you kids make mistakes, if you know that Gibbs or Carnot also made mistakes, it's very comforting. And you think you can also be a Gibbs in spite of the mistakes that you make. Of course, they did more than their mistakes. They also did a lot of good things. But nevertheless, it's very reassuring that they are very human. So I'll talk about work and equilibrium, which are the only two topics on which thermodynamics for chemical engineers is important, especially the kind of results that you get are all classified as under work or under equilibrium consideration. Talk a bit about work of separation, then thermodynamics and market realities. That's because we all think that thermodynamics is a subject that has to be passed in the second year and then forgotten. The actual fact is that if you plot the work that has to be done in order to produce a pure substance from the mixture in which it occurs in nature against market prices. One is taken from a chemical technology book, the other number is taken from a trade journal. And you plot these, you get a monitor, you get a straight line, actually a correlation, which is beautiful. I'll show you that. And that's what thermodynamics predicts. And then the slope and the intercept will depend upon the economy, depend on the country, the labor costs and various things. But that straight line is very reassuring. It tells you that thermodynamics is not up in the air, it's actually down in the ground. Then I want to talk a bit about reaction equilibria, and then finally about molecular picture of mixing. I must tell you, classical thermodynamics is completely indifferent to the structure of matter. It doesn't care whether you have atoms and molecules or not. Classical thermodynamics results are derived with complete contempt for the structure of matter. But on the other hand, it also doesn't give you mechanisms. So molecular thermodynamics, on the other hand, gives you mechanisms, and you're able to actually feel what happens in thermodynamics actually, in classical thermodynamics, actually is explainable in terms of molecules and their motions. So I'll start off. The first thing that happens to a chemical engineer, and many of you may have felt that the number of chemicals is infinite, so there's no way I'll know anything about them. Actually, it's not. First of all, it's not really infinite. And secondly, they fall into classes. And in fact, after you've heard Professor Sharma's lecture, he must have given you the whole sweep. He's a walking encyclopedia. And he would have given you the entire sweep of chemical industry. You do get a complex when you listen to Professor Sharma. You think there's no way I'm going to know all that. And that's probably true. He is an exceptional person. But coming back here, you have really four classifications into raw materials, major fuels, bulk chemicals, and specialty chemicals. And up to the bulk chemicals, you have 300 intermediates, but 20 major base chemicals. So really, it's not so infinitely large. It's not intractable. One of the problems with chemical engineers is very often, I don't know about UPES, maybe you do a better job of it than most institutions, including IITs, we don't give them enough chemistry background. In fact, chemical engineers often know more physics and mathematics than chemistry. The chemistry is taken for granted. I mean, if the chemist can make it in the lab, we ask how can we make it in the industry. Its scale up is the major problem. Let me get back. This is a chemical industry. This is typical of a thermodynamics guy. Particularly if you're not good at sketching, take to thermodynamics. You can draw circles and get away with it. You just label it. So you have a reactor usually at the heart of an industry, chemical industry. You have a separation and recycle system. Then you have a heat exchanger network and utilities. I don't know how many of you have gone to the chemical industry. If you have, if you go to a refinery, for example, the first thing that you notice is it's full of pipes. In between there are some equipment. The miles and miles of pipes. But all of this has to do with optimization. You make sure that the energy is not lost, you recycle things and so on. So this is really a typical chemical industry. And if you look at industrial separation processes, this figure is actually an old one, but I have verified that the numbers are approximately the same even now. You have separation process. Even if you have a reactor, you finally produce a mix of substances and you have to separate them. And when you separate them, 55% of them are what I describe as equilibrium separation processes. What happens in these processes, for equilibrium to be reached, you have to give a lot of contact time. And it turns out in practice, some processes are so fast that they reach equilibrium, near equilibrium very soon. So in those cases, actually thermodynamics will provide you the basis for design itself. Then there are rate-governed separation processes. and then mechanical separation processes, which are separately. So rate governed separation
Yeah,
process,
चल रहा है किसी
you will
में।
first read about reaction rates or the process rates, or you do transport phenomena. So you cover those in that. But 55% of the processes actually can be designed from thermodynamics alone.
इवेंट चल रहा है।
Thermodynamics and mass balance and energy. So separations are basically expensive. Most chemicals do not occur in the pure state in nature. So separation processes
मुझे नहीं पता।
contribute a major part to the cost of manufacturing of chemicals. And 70% of capital equipment in the petroleum and petrochemical industry is again on separation equipment. So what about thermodynamics? Talked to you about the chemical industry. Extraordinary width of application. I don't know if you know, I can tell you how tall the tree can grow in Dehradun from thermodynamics. All I need to know is the relative humidity in the atmosphere and what the, if I want to make an accurate calculation, I need to know the components in the soil and the water in the soil, what's dissolved in it. It's a very simple calculation. In fact, if it's an ideal case, you will simply get the height of a tree, the maximum height to which a tree can grow is RT by mg into log of the relative humidity. And so you can actually calculate this. You might say, what use is it? First of all, it's beautiful, so you can't ask matlabi questions like what use is it? And it's nice to know that you can sit in the lab and say the tree shall not grow taller than this. You're playing God a bit. And it works, you can verify. The second is you can ask questions about how old is the universe. The universe expansion, when Penzias and Wilson discovered that the temperature out far in the universe is 3 degrees K, one of the things they did, they came back to thermodynamics and said the universe is like an ideal gas because the planets are large, but they are so far between, the space between is so large, it's as good as non-interacting systems. If it's a non-interacting system, it should obey PV per gamma is equal to constant. And so, if you know the temperature at some initial stage, then it's gone to 3 degrees. By the expansion, you can calculate how big the universe has become. You can ask how large is the universe, and if you assume a rate of expansion, then you can calculate the age of the universe. That's how they do it. So thermodynamics basically plays a supervisory and often intangible role in engineering. It sets the boundaries of design. It tells you what the limits are. It's almost like a grandmother telling you not to play outside this field. But it's a very strict grandmother. You can't disobey its laws. It sets the limits really. In chemical engineering applications, it's really phase and reaction equilibria. Separation work is what you can calculate. You can calculate the maximum work you can get from a device. You can calculate the minimum work you can get away with. Now, I do encourage, in some form, laziness in students. But I suggest intelligent laziness. You reduce the time required to do something. But usually what happens in our universities is students work, but they hide the fact that they work because it's a great premium to be able to get marks in the exam without working. So what you do is turn all the lights off, pretend you go to sleep at 9 and then get up at 10 and keep a small light there and study till 1:30 or whatever and then get marks in the exam, and then everybody says, oh, this kid is so smart, he got marks without working. But actually it's the work that's important. In the long run, it's the work that alone gives you dividends. Sorry, that's the teacher in me, I can't help more. Teaching to you from time to time. But the last is design of equipment in near equilibrium process. The famous McCarthy diagram by which you design your distillation columns and all that assumes that the process reaches equilibrium, otherwise it reaches close to equilibrium. And this is something that I want to tell you about. This is from Lewis. There is a beautiful thermodynamic book by Lewis and Randall. It's a little verbose, but it was written. Lewis was probably one of the greatest expositors of thermodynamics after Gibbs. And I think 6 of his students he was a chemist, and 6 of his students got Nobel Prize. He didn't, actually. And he should have. By all reckoning, most chemists will tell you Lewis was a great man. In his preface to his thermodynamics book, he writes, and these are the words, he says, when you visit an ancient monument, you see only the perfection of the completed whole. Enter such an edifice that is still partly under construction, you realize that these great structures are the result of extraordinary human effort given a direction and purpose. And this is a remarkable statement, and he says that about thermodynamics itself, because classical thermodynamics is such a complete subject. It sort of frustrates you also. Because if you try to do research in classical thermodynamics and try and get a result, new result, and then you go back to Gibbs's old manuscript, there will be a footnote that says this can be easily shown. And then you discover easily shown means 20 pages of algebra. After you've done all the thinking, you can come up with that result. But it's such a complete and perfect document. Gibbs's original book is absolute masterpiece. I'll tell you a little more about Gibbs. But essentially, because of that, you don't realize that this was done by hard work. People thought about it. It was centuries of thinking that finally became consolidated into this perfect whole. And he says, you should realize if you went back through history to the construction process, then you will realize that this was actually put together with a great vision. And the purpose in all this, like in all of university efforts, is to find unity in knowledge. You ask if diverse phenomena can be explained with a few principles. And that's the same question that's asked here also. It's instructive to know some of the masters who gave direction and purpose to the edifice of thermodynamics. So I'll show you some pictures and tell you a bit about them. If you start with history, really earliest you have to start is Galileo Galilei. And he really introduced the scientific spirit. You know, what happens now in scientific theories is if you postulate a theory, you have to postulate along with it an experiment, a possible experiment that may lead to its downfall. You know, like Einstein, for example, when he came up with the general theory of relativity, he suggested that the bending of light during a solar eclipse should be measured. And Eddington went to South Africa 2 years later, actually made this measurement, came up with an answer that was exactly what Einstein predicted. But if that experiment had failed, the general theory would have been thrown out. But this idea that a good scientific theory must come with an experiment that can test it at its limits came from Galileo. Before that, we didn't have it. And in fact, I have an interesting story in that. In both the Greek and Indian traditions, what we did was we used our left brain and collected a lot of data, and we didn't understand it. Then we went to a sage. We didn't use our right brain to explain the data. We went to a sage and said, "Sir, I'm very confused, you please explain." And then the sage explained it. And after the sage explained it, you didn't really accept his explanation, but you dare not question it because he's a sage. The famous anecdotic example is that of Aristotle. You know, he made a statement in 260 AD that women have fewer teeth than men. And then it was 1410 AD before somebody had the guts to say, no, Aristotle was wrong. I have counted the teeth of many women and many men. They all have the same number. We have to find some other way for being superior. You can't do it with teeth, number of teeth. So this, and mind you, Aristotle had 2 wives. He never did the experiment of counting their teeth. But anyway, Galileo introduced the scientific spirit. We take it for granted now. We take it for granted that we postulate theories and experimentally verify them. Isaac Newton, of course, was outstanding. I'll come back to Newton a bit. And Newton, in thermodynamic context, he is the one who told us how to calculate work. You know, work being the product of the force and the distance moved by the point of application in the direction of the force. So that was Isaac Newton's idea. And then Sadi Carnot was a very young man when he died, but he came up with the second law before the first law was discovered. And he came up with the idea of absolute temperature. I'll share a few more ideas with you of Sadi Carnot in the next few slides. Joule came up with the conservation of energy. I have some more to say about Joule as well. Rudolf Clausius came up with the idea of entropy, actually the definition of entropy. The idea of entropy was hidden in Sadi Carnot's analysis. It was Clausius who postulated it. Here are some pictures. Unfortunately, people take pictures of famous people only when they become famous and they're old. And they don't take pictures when they're young, so it's very hard to find people when they're young, pictures of people when they're young. And that's the youngest picture I could get of Galileo on the net. And this is Newton. And Newton discovered the laws of calculus, the laws of gravity, motion, optics, and then turned 26. Don't give up, you know. Many of you are younger than that, so you can still try. But you may not succeed in all this by the time of 26, but you can push it a bit. It doesn't matter if you discover all that when you're 60, it's still very, very admirable. Then Carnot and Clausius. Carnot was a French engineer scientist. In fact, it is said that he is the only engineer who contributed to fundamental science in such a fundamental way. And I say such a fundamental way because the second law of thermodynamics has been touted by many scientists as the greatest discovery of human beings. In fact, Eddington I don't know if you know Eddington. Eddington is the one who verified Einstein's general theory of relativity. Very arrogant man in his own way. But he's supposed to have said if all the laws of the universe are lost except the second law, chances are in 10 years we'll reconstruct all of it. We said second law, it's very uncertain whether we'll get anywhere till somebody actually discovered the second law. So that's Carnot. And then this guy is the neologist. Neologist is one who finds the right name for things. And he sort of came up with many names in thermodynamics, including the word entropy itself. He is a mathematician. Look at the nationalities, the different people. So the ideas, here's a summary of ideas of these two people. Heat to work interconversion is asymmetric. You can convert it one way, but the other way there are some constraints. Second is he introduced the idea of a heat reservoir. The only heat reservoirs we know when we are destroying their nature is the ocean and the atmosphere. But now we are putting in so many changes, we are dumping so much heat in the environment that these are no longer heat reservoirs, the thermodynamic state itself is changing. In thermodynamic absolute temperature, he came up with this beautiful idea that the efficiency of a Carnot engine that he introduced was actually a ratio of functions of temperature, monotonic functions of temperature. He called them the absolute temperature, and by applying it to an ideal gas cycle, he actually showed that the absolute temperature is in fact proportional. Absolute thermodynamic temperature is proportional to the absolute ideal gas temperature. You must recall that the ideal gas temperature was done by Gay-Lussac, who had measured volume changes of gases, and he extrapolated to a temperature where the volume would be zero, and he said that's the lowest temperature you can reach. And these two are proportional, and it's the luck of students that the proportionality constant was set at 1. Otherwise, we professors will trick you all the time. We'll say thermodynamic absolute temperature and you lose the ideal gas temperature and you will get the wrong answer. We could have made it easily 2.35 or something, which is the proportionality constant, but it was historically chosen to be 1. So you're very lucky. You can get very confused and still get the right answer. I think this is something I didn't ask for. Can we get into this Facebook stuff? No. I want the other one. You got rid of the main thing. No, just press the into there. Yeah. And go back to the slide. I didn't know Facebook interfered in seminars. So he talked about efficiency of a reversible Carnot engine. Very remarkable for a person in 1830s. There was Otto, Diesel, all these people were discovering various engines of more and more greater and greater efficiency. He asked the question, regardless of the working fluid in the engine, can I answer this question? What's the maximum efficiency of conversion that you can achieve? And he answered it too. So first asking the question is the most important part of scientific investigation. And he came up with a Carnot engine that you're all familiar with, between two adiabatics and two isothermals. And he said two heat reservoirs, T1 and T2, and he said the efficiency was 1 minus T2 by T1. He said no engine can be more efficient than a Carnot engine. That's actually the second law. In various forms you can state the second law. And then Clausius came up with this definition, that dq by T, where delta Q is actually a function of path divided by the absolute temperature, defines a quantity S, which is a function of state. You must remember, functions of state are far too important in thermodynamics. A function of state is something, if you can describe the state by a certain number of variables, if I can repeat those exact values elsewhere, then I can reproduce the system. You can't reproduce a human being because the human being carries tremendous memory. So functions of state are used only to describe systems in which there is no memory. In fact, that's why we can't do thermodynamics of human beings, but you can do thermodynamics of very large number of human beings. Because on an average, the behavior can be predicted.